Good evening, dear students. Today we will try to understand what inverse Laplace transform is, right? Inverse Laplace transform. Okay. Like we have seen that Laplace transform of a function f t is given by a function of s defined by the operation e to the power minus st ft dt, right? This is what Laplace transform of a function means. So the function of the inverse Laplace transform is to work on the Laplace transformed function, undo the effect of Laplace transform and give us the original function back. So what I mean to say is, inverse transform will work on the Laplace transform of the function and give us the original function with which we had started. This is what inverse Laplace transform is going to give us, right? So first let's see the definition of inverse Laplace transform, and then we will move on to solving problems, right? Inverse Laplace transform is defined by the complex integral formula ft is equal to 1 by 2 pi I integration c minus I infinite to c plus I infinite to the power st fs ds. Right? So this is the definition of inverse Laplace transform. You can obviously derive it, but we won't be doing that in our class. You can straight away come on to the formula, right? So this is the integral formula which defines inverse Laplace transform, right? In this formula, the path of integration is a straight line which is given by c plus IR, like you can see from the integrals, and what we do is we change this r from minus infinity to plus infinity. We will come on to that later. Now we will see how we can find the inverse Laplace transform of various functions, right? So in general, we'll come on to this integral later. Now we'll go stepwise. In general, the inverse Laplace transform can be determined by 4 methods, okay? By using 4 methods. The first one is by using partial fraction decomposition. Second is by using convolution theorem. We had gone through convolution theorem in the last class. Third is by contour integration of the inverse Laplace integral. Fourth is by Heaviside expansion, okay? We will mainly focus on the first 2 methods. We will try to use the first 2 methods mainly to find the inverse Laplace transform of various functions. Then we will have a look at contour integration, that not in much detail. In detail we will be studying only these 2 methods, but obviously we'll have a look of how to perform contour integration method to find the inverse Laplace transform, and we will skip this. We won't go for this, okay? So let's begin with partial fraction decomposition, right? Before understanding this method, obviously we know how to decompose into partial fractions, but before getting into the method in details, I would like to recap few important formula which we had already studied in Laplace transform, okay? And we want to find the inverse Laplace, so let's see. Let's have a look at the important formulas. We already know them, okay? Important formulas. We will be using this to do the operation that we intend to do. So, Laplace transform, and side by side we will find out the inverse Laplace transform, okay? First, we all know this Laplace transform of 1 is equal to 1 by s, right? So immediately from this we know inverse Laplace transform of 1 by s is equal to 1, okay? So there are certain functions whose Laplace transform we know, those are very common and we have already derived them. So we will consider that we know the inverse Laplace as well. We will take these formulas as we will take these equations as formulas and we will apply them in bigger functions to find out the inverse Laplace transform, right? So these are the important formulas that we will be writing for inverse Laplace transform, okay? So Laplace transform of 1 is s, so inverse Laplace of 1 by s is 1. Laplace transform of e to the power at is 1 by s minus a. This gives inverse Laplace transform of 1 by s minus a is equal to e to the power at, right? Third, Laplace transform of t to the power n is equal to factorial n by s to the power n plus 1. These Laplace transforms we have derived, and from these derived Laplace transform we can automatically write the inverse transforms, right? Hope it is clear to you all. So if this is the case, then inverse Laplace transform of 1 by s to the power n plus 1 is equal to t to the power n divided by factorial n, right? For Laplace transform of sine at gives me a divided by s square plus a square. From this directly we can write inverse Laplace transform of a divided by s square plus a square is equal to a sine at. Also from there, here we can write 1 divided by s square plus a square gives me a sine at divided by a, right? Fifth, Laplace transform of cos at is equal to s divided by s square plus a square. Therefore you have inverse Laplace transform of s divided by s square plus a square is equal to cos at. These are all known formulas, but still I am repeating these for your convenience sake. Okay. The hyperbolic functions I'm not writing. If it is sine hyperbolic at, it becomes a divided by a square minus a square. Similarly, if it is cos hyperbolic, it becomes a s divided by a square minus a square, right? That is the only difference. You have a minus in place of plus, okay? Now Laplace transform of e to the power at if t is equal to f of s minus a. It is very important. We will require it very frequently. So inverse Laplace transform of f to the power s minus a is equal to e to the power at ft, right? If we try to apply this formula, we will be, let's apply this to certain functions. Say Laplace transform of e to the power at sine bt, let it be b, it can be a as well, anything. So Laplace transform e to the power at sine bt is f of s minus a, right? F of s minus a means the Laplace transform of ft, but the s will be replaced by s minus a. So here ft is obviously sine bt, so the Laplace transform of sine bt is a divided by s square plus a square, but over here the s will be replaced by s minus a. A by a means the coefficient of t in e to the power at. So over here it becomes b minus a whole square. This becomes a b because over here we have sine bt, right? So what we have done is the function over here e to the power at is multiplied with the function sine bt. So the Laplace transform of sine bt is b divided by s square plus b square, but since e to the power at has been multiplied to sine bt, s has been replaced by s minus a, right? So immediately from here we can write inverse Laplace of 1 divided by s minus a square plus b square gives you a 1 by b e to the power at sine bt. Okay. So by seeing the form, you have to understand what formula you are going to use, right? Just a second. Okay. Okay, Laplace transform, and over here the inverse Laplace transform. Okay. So if we want to look at it's 2 Laplace transform of e to the power at cos bt is equal to, first we have to write the Laplace transform of cos bt, and it is nothing but s divided by s square plus b square, and since over here we have a e to the power at multiplied to it, we have s minus a whole square plus b square, right? And this s will be replaced by s minus a. So this is the Laplace transform of e to the power, just a second, e to the power at cos bt. So from here obviously we can write the inverse, therefore the inverse is given by inverse Laplace of inverse Laplace of s minus a whole square plus b square gives you a e to the power at cos bt, right? Okay, so third, let's write it for hyperbolic as well. Laplace transform of e to the power at sine hyperbolic bt gives you and since it is sine, so over in the top we have b, and over here we have s minus a square minus a b square, right? So the inverse Laplace is given by inverse Laplace of 1 divided by s minus a square minus b square is given by 1 by b e to the power at sine hyperbolic bt okay, Laplace transform of e to the power at cos hyperbolic bt is given by s minus a and s minus a square minus a b square. So obviously the inverse Laplace is given by s minus a divided by s minus a square minus b square is equal to e to the power at cos hyperbolic bt. Okay, and last we'll be writing a very important formula which you will require very often maybe. That is, we know Laplace transform of t f t is equal to minus d ds fs, right? We have derived this formula, that is the, if you move on to the section where we have found the derivative of Laplace function, right? This is nothing but the derivative of Laplace function, Laplace transform, right? So from here we can write, if Laplace transform of TFT is this, that means inverse Laplace of this is TFT, right? So we can write inverse Laplace of d ds fs is equal to minus TFT, right? This is what a Laplace transform does. The definition says this. From this you can write is equal to minus t, and ft is nothing but the inverse Laplace of fs, right? Inverse Laplace of fs. So this gives us a very important formula, that is inverse Laplace of fs is equal to minus 1 by t inverse Laplace of d ds fs. Okay. Now why this formula is important, though we have inverse Laplace in both the sides, but it is important because there are certain functions whose form of inverse Laplace is not known to us, but the derivative of the derivative of the Laplace transform is known to us, right? What I meant to say is there are certain functions whose inverse Laplace is unknown to us, that is, we do not get it directly from the formulas which we have written earlier, right? But what happens, the derivatives of the functions, they are in such a form that their inverse Laplace is in the forms that we have just seen. Say for instance, if we are doing a inverse Laplace of tan inverse something, if we want to do the inverse Laplace of tan inverse something, we do not have that in the formula, right? But the moment you do the derivative of tan inverse, you get it in terms of 1 divided by 1 plus s square, and that is like the known form just now which we have found. So it is this formula is very useful in those cases where the Laplace transform of the derivative is known to us, right? Okay, we'll come on to this later. So since now we know the formulas, we will be moving on to the methods of finding Laplace transform, right? So first we will move on to the partial fraction decomposition. Partial fraction decomposition. Okay. So if we have a function fs is equal to ps by qs, if we have a function of this sort, okay, and ps is a polynomial and p and q both are polynomials of s, obviously, and the order and the degree of ps is less than qs, okay, the degree of ps has to be less than qs, only then the method of partial fraction can be applied, and this can be expressed as sum of terms, right? And then we can apply the inverse Laplace formula. Okay, so the only condition that we have is the degree of polynomial ps has to be less than qs, only then can we apply the partial fraction decomposition method to find the inverse Laplace transform of the function, right? So we will have a look at it through various examples. So let's go for example 1. Example 1. Find the inverse Laplace transform of 1 divided by s minus a. Right? So, like you can see from this function, we do not know the inverse Laplace of this whole function, but obviously we know the inverse Laplace of 1 by s, it is 1, and we know the inverse Laplace of 1 divided by s minus a, it is e to the power at, right? So if we decompose it into partial fractions, we will be able to write the inverse Laplace transform of the entire function. So inverse Laplace of 1 by s minus a is equal to you can straight away find it, 1 divided by s minus a minus 1 by s, and a 1 by a comes out, right? So we need to find the inverse Laplace of this. The denominator is s minus a and s, and yeah, it is. So it has come out. Okay, if you want to do this, it is s minus s plus a and a gets deducted, so you get this. If you have problem in finding out this, you can straight away apply 1 divided by s minus a is equal to a by s plus b by s minus a, and then you can perform the calculations, just match the coefficients, you will get this, right? If you have any problem doing it in one line. So since it is a linear function, since Laplace transform and inverse Laplace transform are linear transforms, we can perform it on all the terms of the sum. So it becomes 1 by a inverse Laplace of 1 divided by s minus a minus inverse Laplace 1 divided by s is equal to 1 by a. Inverse Laplace of 1 by s minus a is e to the power at, and inverse Laplace of 1 by s is 1. Right? So I hope you can understand the technique at least. Our technique is we will decompose the functions in partial fractions, and so we can get them in terms the terms will be added or subtracted from each other, and then we can apply the inverse Laplace transform on those individual terms and find the final result, right? So we will do one more example so that you can completely understand what I'm trying to say. Example 2. Find the inverse Laplace of 2 to the power s square plus 5s plus 7 divided by s minus 2 s square plus 4s plus 13. Please practice problems like this. Okay, solution. So have a look at the denominator. We have one function and this is a quadratic which cannot be expressed as a whole square. So in that case we have to write it like this: 2s square plus 5s plus 7 divided by s minus 2 s square plus 4s plus 13 is equal to, since we do not have any power over here, we can write it a divided by s minus 2 plus, since this is a quadratic and it cannot be expressed as a whole square, we have to write it like bs plus c. These are all known methods. If you have forgotten, have a look at your class 12 books. So now all you need to do is just match the coefficients of the numerators, right? Therefore we get 2s square plus 5s plus 7 is equal to a into s square plus 4s plus 13 plus bs plus c s minus 2, right? So just now we have to separate the coefficients of the s terms. So s square is a plus this plus a b. Then the s term you have 4a minus 2b, right? Minus a 2b plus you have a c. And then the constant term, in constants we have a 13a, and over here you have a 2c, right? Minus 2c. So we have separated the coefficients. Now we just need to compare. Comparing the coefficients, we get a plus b is equal to 2, right? This is equation 1. Now this 4a minus 2b plus a c gives me a 5 is equal to 5. This is equation 2. And 13a minus 2c gives me is equal to 7. This is equation 3. So you can solve these equations in any method you want to. Okay, so if you multiply, anyways, I'm just multiplying equation 1 by a 2 and equation yeah, I'm multiplying equation 1 by 2. This gives me a 2a 2b, so I can replace it over here, and equation 2 by a 2. Okay, so I'm putting equation multiplying equation 1 by 2, this equation 1 into 2, and equation 3, these two I am putting into equation 2 multiplied by a 2, right? So you can just replace everything at a time. I have multiplied equation 1 by 2, and then I'm substituting this equation and equation 3 in equation 2 multiplied by 2, right? So I get the 2b and 2c terms, 2b and 4c terms. So over here we get, I've multiplied this equation by a 2, so it becomes a 8a minus a 4b. So 4b gives me 8 minus a 4a, right, plus 2c gives me 13a minus 7 is equal to, I multiply to 10, right? Or 12a plus 13a is equal to 10 plus 8 and 7, it gives me 15. Or so it is 25a is equal to 25, so a is equal to 1, right? A is equal to 1. So putting in equation 1, we immediately know b is equal to 1. Putting in 3, if you put these values in equation 3, I get c is equal to c is equal to 3, right? So a is 1, b is 1, and c comes out to be 3. So since we have got all these terms, now we will put in equation 1. That means fs, this originally was our fs is equal to a is 1 divided by s minus 2 plus s plus 3 divided by s square plus 4s plus 13. Okay. So till now we have done nothing but just decomposed the function into partial fractions. Now we will be applying the inverse transform rules, right? So this is very simple. The first term is very simple. We will do it later. It is just s minus a, so it becomes e to the power 2t, right? This transform is easy. Now over here, what are the things you have to look for, these has to be in s square plus b square form, because that is the form that we all know. So I have to transform this into forms s square plus a constant, right? So what I'll do, s square plus 2s, over here we have 4s, so I multiplied by a 2. To make it a whole square, I add a 4. Since I'm adding a 4, I'm left out with a 9 to make a 13, right? And over here I have s plus 3, I've kept it as it is equal to 1 divided by s minus 2 plus s plus 3 divided by, this becomes s plus 2 whole square plus a 3 square. Okay, now second thing what you will see is over here the s term is added by a plus 2. When these terms happen, that means the inverse Laplace will have a e to the power minus 2t term, right? So the s in the numerator also needs to have this s plus 2 term. So we will write this as s plus 2 plus 1. Right? The 3 we have replaced by s plus 2 plus 1. So you can write it as 1 divided by s minus 2 plus s plus 2 by s plus 2 square plus a 3 square, and then you make it a separate term, 2 square plus a 3 square, right? So now if you're asked to find the inverse Laplace, you already have all known forms, not a single form is unknown. So this term 1 divided by s minus 2 becomes a e to the power 2t, right? Over here it is s divided by s square plus a square form. It is the cos 80 transform, right? but it is translated by 2. That means we have a e to the power minus 2t in front. So e to the power minus 2t cos 3t, because our a over here is 3, right? And over here we have a constant, and s square plus a square form. When it is a constant, it is a sin at form, but it is translated by 2, right? So it becomes 1 by 3, because over here we should have had the a squared a term. A is not there, so we have to divide it by a e to the power minus 2t, since it is translated by 2, and the overall form is of sin 3t. So this is our final answer. So I hope it is very clear how you have to perform all these operations. I'll be giving you, I just give you 2 homeworks and wrap up today's class. Please try to find these inverse Laplace transforms. Find the inverse Laplace of 16 s square plus 2s plus 5 whole square. This is 1, and second 3s divided by 2s plus 9. Please be updated with the class and the homeworks, because very soon I'll be giving you an assignment and you will be time bound. You have to complete and give it to me in a very short span of time. So please practice problems and do not lag behind. Okay, so do this homeworks, and thank you for joining me. Have a good day.